Okay, chapter 5.2, finding theoretical probabilities. In order to understand how to use empirical probabilities to estimate and verify the theoretical probabilities, we first need to learn how to calculate theoretical probabilities. So just as a quick reminder, an empirical probability is something that you get from a simulation like we did on the previous section. For instance, I found that the proportion of heads in my simulation was 4 out of 10. And the theoretical probability we'll find for flipping a coin and landing heads is 1/2, or 5 out of 10. Okay, so again, what we want to do is see if we can use these empirical probabilities to estimate the theoretical probabilities. So number 2, the following are some facts about theoretical probabilities. They're always numbers between 0 and 1, or 0% and 100% if you're dealing with percentages. They can be expressed as fractions, decimals, or percents. If the probability of an event is 0, then the event will never happen. If the probability of an event is 1, then the event will always happen. It's certain. Right, so number 3, we're going to use the following notation to represent the probability that an event will happen. So if we go back to our example from the previous section, we're going to use P for probability and talk about the event of a coin landing heads. So we say that's the probability the coin lands heads is 0.50. And we can express that as proportion, as a fraction, or as a percentage. Okay. If we let A equal the event that the coin lands heads, then we can use this notation a little bit shorter. Probability of event A is 0.50. A sample space is a list of all possible outcomes for a random process. If the outcomes of a random process occur with the same frequency, then they are called equally likely outcomes. For example, the 2 outcomes for flipping a coin are heads and tails, and each occur 50% of the time in the long run. The sample space for this random process of flipping a fair coin is then tails and heads. So this is our sample space. And this set of braces is just some set notation. So it's our set of outcomes. So note, these 2 outcomes are considered equally likely because they both have the same probability of 1/2. We could say that the probability of getting tails is 1/2. And the probability that the coin lands heads is also 1/2. So again, equally likely means they have the same probability. Okay, for number 5, you may want to press pause and give this one a try before you press play again. Since for each of the following random processes, list the outcomes in the sample space and state whether you think the outcomes are equally likely. So for rolling a fair die, our sample space are the outcomes 1, 2, 3, 4, 5, and 6. And since we're told that this is a fair die, we can conclude that these 6 outcomes are equally likely. If it were an unfair die, then we would not know for sure. Selecting a Reese's Pieces candy and recording the color of the candy, our sample space are going to be the 3 colors, orange, yellow, and brown. If you've opened one of these bags recently, you'll know that these are actually not equally likely. One of these colors is more often or has a higher proportion than the other. So these are not equally likely. Orange is more likely than the other 2. And there's a higher percentage of orange candies in the bag than the other 2 colors. And assigning a grade to you in this course, our sample space are the letter grades A, A-, B+, B, B-, C+, C, C-, D, and F. Right. Hopefully you agree that these are not equally likely, that you have control over this. Right. If they were equally likely, you can imagine your instructor flipping a coin or tossing these down the steps and deciding where they land or basing your grade on where they land. All right, that's not what we do. So we'll have to agree that these are not equally likely. All right, whether you win the lottery on Saturday, you either win or you lose. And these are definitely not equally likely, depending on, well, for most lotteries, you're a lot less likely to win than you are to lose. In some lotteries, your chances of winning are even slimmer than others. And whether the Red Sox win the World Series this year, we have the same sample space as above. They either win or they lose. And these, I think we would agree, are probably not equally likely either. There were two teams and that's it. We might decide that that's equally likely, but then we'd have to take into account their skill sets as well. Whether you win the next game of solitaire you play. And we've got the same sample space as above. And unfortunately, this one is not equally likely either. In fact, the authors of a previous textbook that we used said that the chance of winning, or the probability that somebody wins, is only 1 out of 9. Okay, the gender of your first child. Either have male or female. And this depends on who you ask, but we are going to be assuming these are equally likely for a lot of the examples we look at in this class. Okay, and the last one, spinning a fair coin, a little bit different than flipping, but your outcomes are the same. You either have tails or you get heads. And some people argue that this is not equally likely, but we're going to assume it is for our purposes. Okay, number 6, below is the sample space for rolling a pair of fair die. Fair means that each number is equally likely to appear face up when rolled. So first question is, how many outcomes are in the sample space? Since we're rolling a pair of fair die, a pair means 2. Count up every set of 2, we'll find that there are 36 outcomes in the sample space. And press pause to verify this if you're not sure. Are the outcomes in the sample space equally likely? We're told that the die are fair, so we can say that they are equally likely. So we can say yes. Right, so given that, we're going to use the sample space to find the probability of each of the following events. An event is any collection of outcomes in the sample space. When the outcomes in the sample space are equally likely, the probability of a particular event is just the proportion of outcomes in the sample space that make up that event. So for instance, what is the probability that a person rolls a 1 and a 4? So if we go back up to our sample space, notice that this outcome satisfies that, as well as this one. So we've got 2 outcomes that satisfy that event. So our probability then is 2 out of 36, or 1 out of 18. And if you're working in MyMathLab, be careful. They do ask for the reduced fractions. So just a quick refresher. Both of these numbers in the original fraction are divisible by 2. So we break that down, we get our simplified form of 1 over 18. Right, so second question. And press pause at any point to try these out on your own. And then come back, check to see how you did. And second one, we're looking at what's the probability that the sum of the 2 dice is a 7. So rolling a 7, this outcome gives us 7, a sum of 7. This one does. This one does. We keep going up that diagonal. Looks like there are 6 outcomes that give us a sum of 7. So our probability is 6 out of 36, or 1/6. All right, probability of double 6s, just one outcome that satisfies that. So its probability is 1 out of 36. At least 1/6, the probability of at least 1/6 is a little bit different. So now we want to look at everything that has at least 1/6 in it. So all of these outcomes at the bottom have a 6. All of these outcomes on the right-hand side, that last column, have a 6. All right, so note that this one on the bottom, it still counts in our description of the event because it has at least 1. At least 1 means one or more. So if we count, we'll find that there are 11 outcomes that satisfy this event. So we've got a probability of 11 out of 36. Probability of no 6s, kind of the reverse of the other question. So that's going to include all of these other outcomes. So from here on up, there should be 25 outcomes that include no 6s. So notice that these 2 probabilities add up to 1. In fact, they're called complements of each other, and we'll look at that in more detail in the next part. All right, number 7, let's take a closer look at the last 2 events. probability of at least 1 6 and probability of no 6s. These two events are said to be complements of each other. The complement of an event is the event not occurring. In our example, we either get a roll with at least 1 6 or we get a roll with no 6s. We're going to use the symbol A with a superscript of C to represent the complement of an event A. So this is read as the probability of the complement of event A is equal to 1 minus the probability of event A. So check to see if the formula works for our previous example. So remember that the probability that we didn't get any 6s was 25 out of 36, and the probability of at least 1 6 was 11 out of 36. And well, if we convert 1 to a fraction, called 36 over 36, we can check to see, or we can see that the formula does work. Okay, number 8. Often we are interested in studying more than one variable at a time, as well as the relationship among these variables. The words and or can be used to combine events into new, more complex events. So number 9, let's use the following two-way table to take a closer look at this idea. Following two-way table classifies a group of people based on gender and whether they felt that college was a good financial decision. And there's a source here, it's a StatCrunch survey. You can check out the original survey if you'd like. Right, so in this two-way table, notice we have two variables. We've got a variable over here in the columns, which is their opinions about college. And then we've got the gender variable up here. Okay. So what's the probability that a randomly selected person is male? Well, first note the total down here in the bottom. That's how many people were included in this survey. So the probability that a randomly selected person is male, we want to include all of the males from the survey. So the probability would be 557 out of 1,287. What's the probability that a randomly selected person thinks college is not worth it? Well, not worth it is a total of 104 people. So the probability that someone, a randomly selected person, thinks college is not worth it is 104 out of 1,287. Right, third one. What's the probability that a randomly selected person is male and thinks college was not worth it? All right, so we still have a total of 1,287 people, but now we want to know who fits into both of these categories. So we've got male. Right, here's our male group here. And then the not worth it is here. We want to know the intersection of these two. So that's right here. There's only 57 people that have both of those characteristics, male and thinks college is not worth it. And the last one, what's the probability that a randomly selected person is male or thinks college was not worth it? Now we've got to include the 557 people that identified as male, plus the 104 people that said they didn't think college was worth it. But we also have to subtract the 57 people that had both of these characteristics because they were counted twice. They're counted once in this number, they're counted once in this number. Right, so we're getting rid of the overlap with that subtraction. And that again is out of a total of 1,287. That gives us a total of 604 out of 1,287. Okay, so let's use a Venn diagram to help us visualize these new, more complex events. So let's start off with how a Venn diagram works. So the rectangle represents the sample space. So here's our rectangle. Imagine that this includes the 1,287 people from our survey. Circles represent events. Right, so we might call this event A and event B. The intersection of the two circles represents the outcomes that belong to both events. So here's our intersection. And the areas of the circles have no numerical meaning. Larger circles do not indicate more outcomes. Right, so as an example, the word and again creates a new event out of two other events and consists of only those outcomes that are in both events. So what is the probability that a randomly selected person is male and thinks college is not worth it? So here are two events. So we've got male, college wasn't worth it, so we'll just put not worth it. Remember that the entire sample space includes 1,287 people. right? And means we're looking at the intersection in between them. So remember that there were 57 people included in that intersection. So we have a total of 57, and 57 out of 1,287 gives us the probability. Okay, the word or creates a new event out of two other events and consists of all outcomes that are in in either event or both events. So what is the probability that a randomly selected person is male or thinks college is not worth it? So we've got the same two events as above. We've got the same size sample space, 1,287 people. But the or means we want both. So we want both the males or the people that said it wasn't worth it. So if we look more closely again, we know that there were 57 people in this intersection that had both characteristics. That means the 557 males, if I take away that 57, there were 500 males that thought otherwise, that felt that college was either worth it or they weren't sure. Look over here, we know there were 104 people that said college wasn't worth it. We take off the 57 that were male, that leaves us with the 47 females. Right? So, or we can either do what we did before, take 557 plus 104 minus the overlap. Oops. Or we can take the 500, that first section of the Venn diagram, plus the 57 in the overlap, plus the 47 in the right-hand side. And if we add those together, we should once again get 604 as our numerator out of 1,287. Okay, number 11, we're going to use the Venn diagram to help us visualize a few more events. The two-weight table is shown again below for convenience. Right, so first question, what's the probability that a randomly selected person is female or thinks college was worth it? So we're looking at females as one of our events, and college was worth it is our other event. And again, we have 1,287 people in our sample space. So for females, we have a total of 730 females. Was worth it. We have 985 people that said college was worth it. All right, now our overlap are 582. So if we want to figure out how many are in the other portions of this Venn diagram, I'm going to do 730 minus 582. Gives us 148 females that felt otherwise, that were unsure, said no, it wasn't worth it. Now over here, 985 minus 582 leaves us with 403 people, 403 males that felt college was worth it. Okay, so back to our original question, we want to add up those three segments. And we get a total of 1,133 out of 1,287. Okay. Next thing, mutually exclusive. These events have no outcomes in common. It's impossible for both events to happen at once. So what is the probability that a randomly selected person thought college was not worth it or was unsure that college was worth it? So not worth it is one of our events. And this was unsure. This is our other event. And notice that people had to choose one or the other, so there's no overlap here. That means they're mutually exclusive. So in that case, we can just look at the 104 people that said it wasn't worth it and add that to the 198 people that weren't sure. So we get a probability of 302 out of 1,287. And again, note here that there's no overlap. So next question, how do we find these probabilities if we don't have a two-way table? We can use one of the following formulas. And note that these formulas will be given to you. You don't need to memorize them. All right, so first one says if you want the probability of A or B happening, you need the probability of A plus the probability of B minus that overlap, the probability of A and B. If it's mutually exclusive events, then it's almost the same thing, but we don't need to include that overlap. So probability of A or B is just the probability of A plus the probability of B. So we're going to use these formulas to confirm our answers to number 11. Right, so I'm going to take a brief pause, write those in, and we'll. Okay, so first one in number 11, we were looking at the probability that female or that they thought college was worth it. I'm going to say female is F and college is worth it is Y. So using our formula, we're looking at the probability of a female or something's female plus probability they say yes minus that overlap, female and they say yes, it's worth it. So with those two probabilities down below, and notice since they have the same denominator, we can just add and subtract our numerators. And if we check, that was the same thing we did in number 11. Got to go back a page. Okay, so let's see if we can find that. Okay, so that's what we did right here. And the second one, I'll write this in, let's say, to the right of this. So this was the probability of either person thought college wasn't worth it or was unsure. So we'll say probability of not worth it or U for unsure. So we just need the probability of each of those individual events. So we got 104 out of 1287 plus 198 out of 1287.